Okay, good morning. So this is the lecture 3.2 on our group theory course. Is the second lecture of chapter 3. Today we finish chapter 3, which is about characters and character tables. And in the previous lecture we have discussed many properties of characters, which are simply the traces of representations of the group. And we introduced the concept of character tables, which is very useful to work with group theory, and we're going to use them a lot, the character tables. And today I'm going to start working out some examples on how to set up or how to construct character tables. If you think about the character as a trace of a matrix representation, you might think that perhaps the way to do it is to first to find the group representations, and then take those matrices and take the traces and construct the characters. But that's not actually the best and the easiest way to construct character tables. As we are going to see, the easiest way to construct character tables is by using the properties, the orthogonality properties especially, that we discussed last time. So and we are going to work with a simple set of rules that allows us to construct character tables. In many practical cases, we won't need to do that in real life, because for most groups the character tables have already been found, and they are tabulated in textbooks or articles. But it's important to know how to build them, and maybe in some cases it will be necessary to construct a character table from the start. All right. So, as I said, there's a simple set of rules that we can use. The first one, and perhaps the most important one, is that the number of classes is equal to the number of IREPs. IREPs is a short for irreducible representations. So the number of classes is equal to the number of irreducible representations. We have seen that in the last lecture. And that means that the character table is a square table. It has a same number of columns and rows. All right? Okay, and the second property is this. So this equality. Age is the order of the group, and this is a summation over the dimensionalities of irreducible representations squared. So most of the times, using this equation, it's enough to find out what are the dimensionalities of IREPs. Remember that there is always this 1D representation, which is the identity representation, meaning all the characters are 1 for all classes. So again, let me use the group P3 as an example for that. We have discussed this group in many examples. This is a group that it's isomorphic to the symmetry operations of an equilateral triangle. And if you remember, the group P3 has three classes, and then because of this property here, it must have 3 irreducible representations. And the 3 classes are the identity, which is in a class by itself, the 3 C2 operations, the pi rotations and 2 C3 operations, which are the plus or minus 2 pi over 3 rotations over the main symmetry axis of the triangle. Okay, so these are the three classes, and because of that we have 3 representations: gamma 1, gamma 2, and gamma 3. Actually, we call it gamma 1, gamma 1 prime, gamma 1, gamma 1 prime, and gamma 2. So this is gamma 1 prime, and this representation is the identity representation. So all the characters are 1. It's a one-dimensional representation. So we can already start building your character table using that property, and also using this equation here. This allows us to find the dimensionalities of the different representations, because this equation means that we have L1 square plus L2 square plus L3 square for the two representations. This is equal to 6. 6 is the order of the group, so H is equal to 6 for this group. And then we know that for the identity representation, this is 1, right? So this is 1 square plus L2 square plus L3 square, and it is equal to 6. And you can see that the only solution to this is L2 equals to 1 and L3 equals to 2. So in most cases you can basically by inspection and by guessing, you'll be able to find the dimensionalities of the two representations. So this is a 1D representation also, and this is a 2D representation. Okay, so all right, so what do we do next? This I have done that already. Let me repeat here what I wrote in the previous slide. This is the character table that we are building. Gamma 1, gamma 1 prime, gamma 2. This is always a rows of ones for the one-dimensional for the identity representation, and the fourth property we can use is this one. The first column is always the dimensionality of the irreducible representations. Why? Because the first column corresponds to the identity operation and the identity class. The identity is always in a class by itself. So, and then the character is just the trace of the identity matrix, and depending on the dimensionality of the representation, we will have we can just write down the traces. For 1D representation, the trace is 1, and for the 2D representation, the trace is 2. Okay. All right. So we have a partial construction of our character table. What can we do next to find the other elements? We can use this result, which is actually a special case of this more general result that we have seen in the previous lecture, which is the wonderful orthogonality theorem for characters, and this works for orthogonalities between rows, different rows of the character table. Okay, this is the general result, and this is simply a special case for this result when you take one of the representations to be the identity representation. So if you choose, for instance, gamma I in this equation to be gamma 1, which is the identity representation, and you get this equation. So this equation tells us that if you sum over a single row, the sum of all characters times the number of elements in a representation must be equal to 0. Okay. In many cases, this is sufficient to find out what the other characters are. For instance, let's apply this rule to the representation gamma 1 prime. So you can see again by inspection that the only way to satisfy this equality here is by choosing here to be -1 and here to be 1. Okay, then you can see that 1 minus 3, remember you have to multiply this by this, the number of elements in the class. 1 minus 3 plus 2 equals to 0. Okay. Alright, so what else can we do? In some cases we will need to use this full equation, but for this simple group this is actually not enough. Let me use a different rule. The 7th rule is this one that we have also discussed last time, which is your second orthogonality theorem, the orthogonality theorem for columns. All right, so that means that two different columns of your character table, they must be orthogonal. Okay, so let's apply this to these two columns. The classes E and 3C2, and you can see that if I multiply this element by this element and sum this element by this element, this is already 0, right? 1 minus 1 is 0. So the only way to satisfy this orthogonality is to set this to be 0, and for the same reason, the only way to satisfy the orthogonality between the first column and the third column is to set this one to be -1. Okay, so this is a simple example that shows that using this set of rules that we determined in the last lecture, we can construct most character tables. This is the example for the group P3. Okay, let me do another one. Let us do the now an abelian group, the group C3. I'm going to talk about the notation. I'm going to talk about the notation of different point groups still in today's lecture, but initially let us just accept the fact that the so-called group C3, it's a group that has only three asymmetry operations. It has the identity, the C3, rotation by 2 pi over 3, and the C3 square, which is a rotation by twice the angle, by 4 pi over 3. The abelian group, it's interesting because first of all, it allows us to work out an example in which the characters are not real numbers. Now, as we're going to see, the characters are going to be imaginary, complex numbers. And it's also interesting in this case that in this case you see that these two operations that in the P3 group they were in the same class. For the abelian group C3, they are in different classes. So for abelian groups, as we discussed, all elements are in a class by itself. We have only classes with one element only, and therefore the number of classes and the number of irreducible representations is equal to the order of the group. So this group is of order 3. The number of elements is 3. This is the multiplication table. Okay, so we can check that this is correct. So for instance, C3 times C3 is C3 squared, and if you apply C3 and C3 squared, you get the identity again. So it rotates by 2 pi, so you get the identity. So this is a very simple group. I'm sure you'll be able to figure out this character table. If you are curious about what physical system this group corresponds to, there's an interesting way to analyze this is by using the so-called stereograms or stereographic projections. I'm going to talk about them a lot in today's lecture, but just to introduce them, this is an example of a stereogram for the C3 group. You can think of it as an object, or if you will, as a molecule in which you have a sphere, and this is a projection of points that are in the surface of the sphere. This is the projection in a plane, in a horizontal plane, in this plane that cuts through the center of the sphere. In which, when you have a cross or a plus sign here, this means that these atoms or points that are above the horizontal plane. If you had an open symbol, open circle instead of a cross, if you had an open symbol, it means that these points are below the horizontal plane. Okay, so, and also in this sphere you have an object here in the center of the sphere, which in this case it's a triangle, and you can see that by combining the positions of these dots and the shape of the triangle, you can see that the only operations that you have in this case are these rotations. You don't have, for instance, reflection planes in this particular case, because you see that the reflection will take the points into themselves, but it will change the orientation of this triangle. So this is not a symmetry operation. Okay. So this is a stereogram for group P3. So let's try to work out the character table for this group, for group P3. So let's use again the properties that we described before. First of all, we have 3 classes, because it's an abelian group with 3 elements, so every element is in a class by itself. So the 3 classes are identity, C3, and C3 squared. And because of that, you have 3 IREPs, 3 irreducible representations that I can call gamma 1, gamma 2, and gamma 3. Gamma 1, gamma 2, and gamma 3. As we saw before, I can fill this with the 1s. This is the identity representation, and also this column, it should also be 1. Okay, because all the representations are one-dimensional. And then my goal here is to find these 4 elements, A, B, C, and D, that are at this point unknown. Okay, so these are unknown, and if I use the orthogonalities between rows, if I use the orthogonality between this and this row, I get this equation: 1 plus A plus B must be equal to 0. And if I use the orthogonality between the first and the third row, I get another equation which is very similar to the first one: 1 plus C plus D equals to 0. Okay. So what else? I also know that the characters, in this case, they are, since the representations are one-dimensional, the characters must obey also the multiplication table of the group. So for instance, if I take a square, because a is a representation, 1D representation of C3. So if I take a square, I must get C3 squared, which is in this representation is b, right? So a squared is equal to b. And for the same reason, a squared b, or sorry, ab is equal to 1. AB is equal to 1 because it corresponds to rotating by 2 pi over 3 and then by 4 pi over 3. It must give me the identity, right? And by combining these two equations, I get a to the cube is equal to 1. So a to the cube is equal to 1. So in principle, that I could have 3 solutions for this equation, right? I can get e to the I 2 pi over 3, 3 complex numbers, e to the I 4 pi over 3, and a is equal to 1 is also a solution. But you see that if I choose a equals to 1, I won't be able to satisfy this equation and these two equations. Maybe it's not so obvious, but you can test that. This is I'm going to disregard. And you will see also that choosing a equals to e to the I 2 pi over 3 or a e to the I 4 pi over 3, these are two equivalent choices that basically will correspond to interchanging or swapping these two rows. So in one case, as we're going to see, a is going to be equal to e to the I 2 pi over 3. This is the solution I'm going to use. And in the other case, c is going to be this one. But we don't know that yet. But let me just choose this solution and let's see where does it lead us. Okay, so let me choose a is equal to, I will call it omega, which is equal to e to the I 2 pi over 3. Okay, if that's the case, then b is a squared is equal to the I 4 e to the I 4 pi over 3. And this is good because it already satisfies this equation here. Okay, why? If you look in the complex plane, these are 3 vectors in the complex plane. 1 e to the I 2 pi over 3, e to the I 4 pi over 3. The sum of these 3 complex numbers is 0. Okay, so this is allows me to find a and b, and using the same argument now, considering the orthogonality in between these two columns, you can easily check that the c then is going to be omega squared and d is going to be omega. That's the only possible solution. You can check that out if you want. Okay, so the character table for group for the group C3, and let me erase here. I don't know if that's the best thing to do, but let me do this. And so the character table, it's omega, omega square, and omega. And you can verify that all the orthogonalities are satisfied. Okay. Again, this is interesting because it's the first example that we see in which the characters are complex numbers, and this is going to happen whenever you have a cyclic group like this one, which is an abelian group. So this is the second example I wanted to discuss with you. Okay. So as I said, the character tables are well, people in the past, they have worked out almost all the possible examples, and therefore you can find them in textbooks, and especially in our textbook, you can find them in the Appendix A of the textbook. Let me show to you where it is. So let me get this. If you look into our textbook, you see the Appendix A. You have the very many different character tables initially for the so-called point groups. Point groups are a very important set of groups for molecules and for solids, in which you apply symmetry operations, and at least one point of your object, or if you want one atom of your molecule, remains invariant and it doesn't change. Okay, these are not all the possible groups, but it's a very important subset of possible groups, which are called point groups. We are going to discuss a lot point groups. So these are the character tables for many different point groups. So they are all for your reference in the Appendix A of textbook, and you're going to use them a lot for doing exercises. Even in today's lecture, we're going to use these character tables a lot. Okay, let me go back here. Okay, so right, okay, let me just check one thing. Okay, another thing I wanted to discuss here is notations of symmetry operations and point group notations. So and there are different notations for point groups and for symmetry operations. The one we are going to use more in this course is this so-called Chamfli's symmetry notation. In this notation, as we have seen already, the letter E represents in most cases the identity. When you have C over N, it's a symmetry operation that it's a rotation up through an angle of 2 pi over N in the main symmetry axis of a molecule. For instance, for example, C2 is a rotation of 180 degrees, C3 is a rotation of 120 degrees, so on and so forth. For molecules and solids, most of the cases we're going to see corresponds to rotations of C2, C3, C4, and C6. So we typically don't have in condensed matter rotations about angles of 2 pi over 5. You see that you have n equals to 1, 2, 3, 4, and 6, but you don't have 5. You can have molecules, as we're going to see, with symmetry axis, 5-fold symmetry axis, rotations of 2 pi over 5, but you cannot have that in a periodic solid. And the reason for that is you can understand it in a simpler way. It's related to the fact that you cannot fill a plane with pentagons, like in this plot here. You cannot fill a plane with pentagons. There's always some missing spaces, and for that reason you don't have any Bravais lattice with a rotation symmetry of 2 pi over 5. Although in 1984 people discovered quasi-crystals. Quasi-crystals are intermediate structures between crystals and amorphous systems, in the sense that they are not periodic, so they don't have long-range translational order, but they have orientational long-range order. And surprisingly, in 1984 they found that quasi-crystals, they have very sharp X-ray diffraction peaks, which is a signature of long-range order, but they had five-fold symmetry, rotational symmetry. So this is again this is an example of a two-dimensional quasicrystal. You can see that it's not perfectly ordered in the sense of translations. That's not a single building block that you repeat and it generates the whole crystal. But you can see that you have five-fold rotation symmetry about certain axes. So these are special cases that we are not going to discuss a lot in this course, but just to let you know. But for molecules, you can have icosahedral symmetry, as we're going to see. For instance, the C60 molecule, the carbon fullerene, it has 2 pi over 5 rotation axis. But for solids, you cannot have those. Okay? So this is just a small discussion about quasicrystals. Let's go back to the notation. We use the letter sigma to indicate reflections, but you can have many different kinds of reflections. For instance, sigma h, when you have a symmetry operation indicated by sigma h, that means a reflection in a horizontal plane. A horizontal plane meaning the reflection plane is perpendicular to the axis of the highest rotational symmetry of the molecule. You're going to see examples of that, and then it's going to be easier to understand. And when you have sigma v, it means a reflection in a vertical plane. The vertical plane contains the axis of highest rotational symmetry of the molecule. Okay? You can also have what we call sigma d planes, which is dihedral planes or diagonal planes. So these planes, they are also vertical, but it's a special case in which, okay, for instance, let's consider this example. Z is the main symmetry axis of the molecule, but also besides the main symmetry axis, you have also secondary symmetry rotation axis in a horizontal plane that we call the xy plane. For instance, x and y could be two symmetry axis in which you have rotations by 2 pi over 2. Okay, so and in some cases you can have reflection planes that bisects these two x and y axes. These are called dihedral or diagonal planes. Again, we're going to see examples of that. So what else can we have? I, when you have the symbol for inversion is I. Inversion is a symmetry operation that takes x to minus x, y to minus y, z to minus z. We can have improper rotations, as we have seen two lectures ago. An improper rotation symbolized by Sn is when you have a rotation by 2 pi over n followed by a reflection in a horizontal plane. So the reflection is not the symmetry, and the rotation is not the symmetry, but the combination of rotation combined with the reflection, it's a symmetry. As we have seen this in the 2 lectures ago when we discussed the symmetries of the tetrahedron. We saw that a group of symmetries in the tetrahedral is this improper rotation, Sn, rotation followed by reflection. And you can also have combinations like ICN, which is a combination of the the inversion and the rotation Cn. Okay, so these are the most common symmetry operations in the Chamfli's notation. As I mentioned, the point groups are very important. There are a total of 32 point groups that are consistent with translational symmetry. 32 point groups that you can find in solids, in periodic solids. In molecules, as I said, you can have more. But for solids, these are the 32 points that we can have. And as I said, the character table for all of them are are in the Appendix A of the textbook. Okay, so now I discussed the notation for symmetry operations. Let me discuss now in the Schonflies notation the notation for the point groups, for the different point groups. Okay. So, for instance, if the group Cn, we have only these 2 pi over n rotations. We have seen this example just a while ago for the group C3, and in which we had only the identity, the C3 and the C3 square operation. This is an example of a more general group Cn. You can have C3, C4, C2, etc. So this is the character table. This is the character table for group Cn. These are the characters. This we have calculated. This we're going to discuss in the chapter 4. These are basis functions associated to each irreducible representation. Don't pay attention to it yet. So, but in this case we have 1D representation A, and we have 2 1D representations that we use the same symbol E in this case. This is not so important, but I can anticipate that. I mean, this means that these 2 1D representations, they are actually related by time reversal symmetry. We're gonna see that in the future. Don't worry too much about that. So that's why we use the same symbol. And in many cases, in crystals in which time reversal it's important, it occurs, then this means that we're gonna have sets of 2D, 2-fold degenerate levels, even though we have only 1D representations for this group. I didn't say that, but we're going to see also that the dimensionality of representation is I mean, the degeneracy of a certain level in a Hamiltonian corresponds to the dimensionality of the representation it belongs to. So this is I'm anticipating a few results that we're going to see in the future. Okay, and this is the stereogram for group C3 that we have seen already. Okay, let's move on. Instead of Cn, we can have groups CNV, in which we have these n-fold rotations combined with the vertical planes that we have discussed. For instance, we have C3V, C4V, C6V, so on and so forth. This is an example for the character table of group C3V. This is a group C3V. As you see, besides the C3 rotations by plus or minus 2 pi over 3, you have also this sigma V, which is the 3 vertical planes that you have. And you can see very clear this in this stereogram. So imagine now that you have the triangle here, and you have the crosses, the points above the plane, but you have 2 of them, and they are related by these vertical planes. When you apply a vertical reflection, you take this point and to this one, and this to this, this to this, on different planes. Okay, so we have 3 different sigma V planes, vertical planes. You can also have CNH groups in which you have n-fold rotations, and now you combine with a horizontal plane, which is the plane of this figure. Okay, so in this case, then you can see that you have crosses and the open circle, and this symbolizes 2 equivalent atoms that go into themselves when you apply the one is above, the other is below the plane of the figure, and they related to each other by this sigma h reflection, which is a reflection through the plane of the figure. So as you can see, you have the different identity, rotations, sigma h plane, and also you have S3 operation, which is an improper rotation, is a combination of C3 and sigma h, for instance. And these are the character table. This is the character table of group C3H. Another possibility is to have n-fold rotation. This is a group Dn. We have n-fold rotations, and we have two-fold perpendicular axis, two-fold rotation axis secondary. Besides the main rotation axis, which is perpendicular to the figure, you have two other. Actually, in this case, you have three more. This is the example for group D3. You have this rotation axis, rotation by pi, by 180 degrees. You can see that when you have a plus sign here, a cross, and the open symbol, when you rotate by pi about this angle, you see that this atom goes to this one, and this one goes to this one. So, and that's the reason, the idea of this C2 prime. You usually call C2 prime rotations to indicate that the rotation axis is different, is not the main symmetry axis of the molecule. Okay, and this is the character table for group D3. And you can have also D and D. In this example, D3D, you can combine that with inversion, and we're starting to see that you can have more symmetric groups. The number of symmetry operations, it's increasing every time, and the stereograms become more complicated, but that's the D3D group. And you can also have D3H or DNH in the more general case. This is the example for the group D3H, in which you have the n-fold rotations plus the C2 prime axis plus the symmetry axis. Oh, sorry, the reflection plane, the horizontal reflection plane. Okay, when we work out this is too much information perhaps, but when we work out examples for these different groups, you will start to get used to them. Okay. So besides these groups, there are other groups with higher symmetry in which you have more than one main symmetry axis. For instance, cubic group. In the cubic system, you have X, Y, and Z high symmetry rotation axis and many other rotation axes. So these are, you can find those character tables in the book as well. For instance, this is a character table for group OH. Group OH is the most symmetric group of the cubic system. It has a total of 48 symmetry operations of the cube. They are all listed here in different classes, different reducible representations, and you can see that in this figure. You can see that you have the C4 axis, X, Y, and Z. C4, in which you have 2 pi over 4 rotations, 90 degrees rotations. But you also have C3 axis that goes through the diagonal. C3 axis go through the diagonals, the main diagonals of the cube. Then you have 2 pi over 3 plus or minus 2 pi over 3 rotations over those axes. You have a rotation axis that goes through the center of the edges of the cube. These are it's in this notation, in this figure is A2, but we call it C2. These are C2 prime axis, and you have very many different mirror planes, so reflection planes. So the cubic group is very. There are a lot of symmetry operations. You can find a very detailed description of the different cubic groups in the pages 52 and 53 of the textbook, and we can use this as a reference because we're going to work out many examples for cubic groups. So just to give you an example, this is a point group of an icosahedral molecule, the C60 molecule, as I said. It has a 2 pi over 5 rotation, so it's not very common, I mean, in crystals, but for molecules you can have this point group, and you can see here that it has a large number of symmetries. It has a total of 120 symmetry operations. So it's a very symmetric molecule, the C60 molecule. So, and this is an interesting example. Okay, as I anticipated, you can have stereographic projections or stereograms it's a way to visualize the symmetry operations of the different groups. They are all tabulated again in chapter 3 of our textbook. We have seen some of them already, but these are the different stereograms. These are all, as I said, in the textbook. Okay, so now that we understand a bit about character tables and about the notation of symmetries in the Schonflies notation, let me work out an example. Let's do problem 3.1 of the textbook as an example. Problem 3.1 actually it's a set of 4 different problems. The problem A, B, C, D. Let's do problem A first, which is explain the symmetry operations pertaining to each class of the point group D3H. You may find the stereograms useful. So I reproduce here the stereogram of group D3H, and this is also the character table. So basically it wants us to write down what are the different symmetry operations of this group. So as we know, E is the identity. What else? Sigma H. Sigma H, as we've seen, is a horizontal plane reflection. Reflection on horizontal plane. But let's see here in the stereogram. These are the, for instance, the sigma H is actually the plane of the figure. Is the plane, so reflection through this plane takes the crosses into the open circles and vice versa. Okay. Okay, 2C3. 2C3 is a plus or minus 2 pi over 3 rotation through the main symmetry axis. So the main symmetry axis is the vertical axis perpendicular to the plane, and you can see that you have 2 pi plus or minus 2 pi over 3 rotation here. All right, 2S3. What is 2S3? This is an improper rotation, right? It's an improper rotation in which you combine a 2 pi over 3 rotation and a reflection through a horizontal plane. For instance, you take a plus sign here. Let's take this one. This one, the plus sign here goes rotate by 2 pi over 3 and reflects through the horizontal plane. Then it goes to the open symbol here. Okay. This is the symmetry operation S3, and you have 2 of those, plus or minus 2 pi over 3. What else do you have? 3C2 prime. 3C2 prime are rotations by pi through the secondary axis to the horizontal axis. Instead of rotating through the main symmetry axis with just one, you have this this C2 prime, this C2 prime. If you rotate by pi, you see that the object or the molecule goes into itself. You have 3 of those, then that's why you have a number 3, the number of elements in this class. Okay. And finally, you have 3 sigma v. Sigma v are reflections through a vertical plane. And these are precisely the same, these planes here that contains this C2 prime axis. So this is a sigma v plane. So you can see that if you reflect through this plane, you recover the same molecule. This is also sigma v plane. This is also sigma v plane. Okay. So this is problem 3.1a. Let's do problem 3.1b. Prove that the following irreducible representations E1 and E2 of group D5 are orthonormal. So this is the character table of group D5. It's an icosahedral group. And these are the 2 irreducible representations that he's talking about, E1 and E2. They are both 2D representations, 2-dimensional representations. And these are the character tables in which alpha is an angle of 2 pi over 5, 72 degrees. And there's an interesting result here, which is you can relate the cosines of 2 alpha and the cosines of alpha to this quantity, which is the so-called golden mean or golden ratio, 1 plus square root of 5 over 2. This is a number which is very important in mathematics. It's actually it's so-called it's the golden mean in the sense that it was known since antiquity as a number related to harmonic proportions in art and in nature. So this is a number that you can see it appears very often when you have 2 pi over 5 rotation symmetry, and for some reason it is also it shows up here as well. So in any case, what we need to do is to see, let's work at this example. It's just to another possibility to work with the properties of character tables. So we have to prove that these 2 irreducible representations are orthonormal. It's just algebra in a sense, but I'll just set up the equations and then you can do the algebra by yourself if you want. So basically what we need to show is that these two rows of the character table are orthogonal to each other. So sorry, these 2 rows are orthogonal. So it means that 2 times 2, which is this 2 numbers multiplied. Remember that you have also to multiply by the number of elements in each class. In this case, it's just 1. Plus 2 number of elements in this C5 class times 2 cosine alpha times 2 cosine 2 alpha. Right, this is a multiplication of these 2 numbers times this one, plus 2 times 2 cosine 2 alpha times 2 cosine 4 alpha, plus 0 equals to 0, must be equal to 0. Okay, so it's just algebra. I'm not gonna do that, but I mean, if you do this and if you do these substitutions here, and you'll be able, if you do this substitution here, this one and this one, you will be able to show this result. So don't worry too much about the algebra. I'm just wanted to get the orthogonality relation so that we can work that example as well. Okay, let's do letter C. Given the group T, the group T is one of the point groups associated to cubic symmetry, is the group of the tetrahedral. Given the group T, and this is a character table, let's verify this equality. So let's see. What's H? H is the number of elements of the group. So we have 1 plus 3, 4, plus 4, 8, plus 4, 12. So H is equal to 12 in this case for the group T. And the dimensionalities of the different representations is 1, 1, 1, 3, meaning that I should show that 1 square plus 1 square plus 1 square plus 3 square is equal to 12, and that's precisely, this is precisely the case. 9 plus 3 is equal to 12. Okay. What else? What is the meaning of the two sets of characters given for the two-dimensional irreducible representation E? So this is, again, we have seen that before for the group C3. Sometimes you use the same letter E to indicate two irreducible 1D irreducible representations that are related by time reversal symmetry. But these are two irreducible representations, and you can see that because it satisfies this equation, right? It satisfies this equation in which you have 1, 1, 1 here. You see that this equation would not be satisfied if you had one irreducible representation and a double dimensional representation and a three-dimensional representation. So that's not the case. So you have 3 1D representations and 1 3D representation. And the final question is if they are orthogonal to each other, or if they are part of the same irreducible representation. Well, I have already answered this question, but let's work out the orthogonality. So they are orthogonal to each other, as they should be, but let's work out the orthogonality between these two representations right here. So this is similar to what we did in the previous example, but just be careful now, because now we have complex numbers. So we need to be careful, because one of the elements in the product, you have to take the complex conjugate, right? So so working out the orthogonality here, I have 1 plus 3. Remember, you have to multiply by the number of elements in the class, plus 4 times. Let's choose this one to be real and the other one to be complex. It doesn't matter. So 4 times omega times omega square complex conjugate star, plus 4 times omega square omega star. Okay, this must be equal to 0 to satisfy orthogonality. Okay, and omega is e to the 2 pi over 3. Okay, so we have 4 plus 4 times omega is e to the I 2 pi over 3. Omega square is e to the I 4 pi over 3. When you complex conjugate, is equal to the I minus I 4 pi over 3 plus 4 omega square e to the I 4 pi over 3 omega star e to the minus I 2 pi over 3. This should be equal to 0. And this is combining these two terms. You have 4 plus 4. You have the e to the minus I 2 pi over 3 here, and e to the 2 pi over 3 there. So I to the minus 2 pi over 3 plus e to the I 2 pi over 3, which is essentially 2 times the cosine, 2 times cosine of 2 pi over 3, which is which is minus 1. So this is 4 minus 4, which is 0. So this works. The orthogonality works. Okay, let's move on. Letter D. Which symmetry operation results from multiplying the operations sigma v and sigma d in the group C4V? So this is the character table of group C4V, and this is the stereogram. There's another question here, which is, can you obtain this information from the character table? So let us do in both ways. Let us first work with the stereogram, and then we work with the character table. So to do that, let me label those atoms here. This is atom 1, 2, 3, 4, 5, 6, 7, 8. And I have to combine sigma v and sigma d. So let's see what is sigma v. Let's try to let's take one particular vertical plane, which is this one. This is a vertical plane, sigma v, and this symmetry operation takes atom 1 to 2 and 2 to 1, 3 to 8, 8 to 3, and so on and so forth. So I can use this notation that we have used that already in the case of permutation groups, if you remember, in which I write atom 1 goes to atom 2. So in the first position here I write 2. 2 goes to 1. 3 goes to 8. 4 goes to 7. 5 goes to 6. 6 goes to 5. 7 goes to 4. 8 goes to 3. So this is a way to symbolize this particular sigma v reflection. So what about sigma d? Sigma d is this is a dihedral plane or diagonal plane, and using the same notation, let's see, 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1, 5 goes to 8, 6 goes to 7, 7 goes to 6, and 8 goes to 5. All right, this is the sigma d, this particular sigma d. So if I use this and combine, I will do first sigma d and then sigma v. What is the result of that? Okay, you can do it by yourself, but let me do just one case. So if you do sigma d, 1 goes to 4, and 4 goes, sorry, 1 goes to, so 1 goes to 3 in this case, because I do first just 1 second. 3, 4, 3, 2, 1, 8, 7, 6, 5. Yeah. So if I combine these two operations, 1 goes to 3, 2 goes to 4, 3 goes to 5, 4 goes to 6, 5 goes to 7, 8, 1, 2. Okay. So and you can see now, you can try to look at these numbers and see what kind of symmetry operation is that. So 1 goes to 3, 2 goes to 4, 3 goes to 5. You can see that it's a rotation, right? A rotation by 90 degrees, a C4 rotation. So this is actually one of the 2 possible C4 rotations that you have in the system. Okay, so sigma V times sigma D is equal to C4. A combination of 2 reflections in this case is equivalent to a rotation by 2 pi over 4. So the second question is, can you obtain this information from the character table? If so, how? Yes, you can. If you look at the 1D representations here, you can see that if you multiply these 2 sets of numbers, you get this number. Okay, so the character tables for 1D representation, they must satisfy the multiplication table of the group. So if you combine sigma D and sigma V, means 1 times 1 is 1, minus 1 times minus 1 is 1, 1 times minus 1 is minus 1, minus 1 times 1 is 1, minus 1. So you can obtain the same result by just looking at the character table for the group. Okay. All right. Okay, so this is one example. Section 3.10, it's the Hermann-Morgan symmetry notation. The Chamfli's notations is not the only notation that you can have to indicate the symmetry operations in the point groups. There is the so-called Hermann-Morgan or international. It's also called the international notation. We're not going to use that a lot, but you're going to see that in many textbooks and articles. So I think it's important to know the correspondence between the 2 sets of notations. But that is in the textbook, is a set of tables in the textbook. So I'm just going to go through a few of them. I'm not going to go through all of them. For instance, when you have a rotation Cn in the Chamfli's notation, in the international notation it's called simply by the letter n. A rotation inversion is n bar. A mirror plane is the letter m, and so on and so forth. These are all the possibilities that you can have. And again, these are all in different tables in the textbook, and you can go through them. For proper and improper rotations, the Chamfli's notation, the international notation in both cases. And the table 3.12, it has all the 32 crystallographic point groups and their symbols in the Chamfli's notation and in the international or Hermann-Morgan notation. In the last column of the table, you have different crystals that belong, or they have these corresponding point groups. Okay, so this is a useful table. The 32 crystallographic point groups, and here also the cubic groups. You can have, for instance, well-known cubic systems like diamond and sodium chloride, and the different crystallographic or notations in the Chamfli's and the Hermann-Morgan. And also in this table you have the icosahedral groups that they do not belong to these 32 point groups, but they are also listed in this table. And these are the different fullerene molecules that belong to the different point groups. Okay, you can use that as a reference. Finally, you can also have this semi-infinite groups which are relevant for linear molecules like CO or CO2. The character tables for these groups are also in the Appendix A. They're also listed there. Why is it called C infinite V? Because if you take this main symmetry axis of these two molecules, you see that you have an infinite number of angles that give you symmetry operations of the molecule. You can rotate, basically you can rotate the molecule around this axis for any angle, and this will be a symmetry operation of the group, and that's why we call it a semi-infinite group. You have an infinite number of rotations about the main symmetry axis. So it's we're going to work with those groups as well, so the character tables are also listed in the appendix. Okay? Alright, to finish this lecture, let me do this problem 3.4 as another example. Actually, there is a misprint in this problem, and that's the reason why I wanted to do this one, because I guess this should be 2 and not 0. Of course, you could do the same problem in which this is 0, but it's not very interesting. Then it would be a trivial problem. So I really think there was a misprint here. So let's do this problem in which this is 2. Okay? So the problem is the following. You have a given representation with the following set of characters. So, and then it gives you the character for the identity, for sigma H, for C3, for S3, for C2 prime, and for sigma V. These are this problem corresponds to the D3H a point group. So and the character table of the D3H group is here. Okay. So the first question is, do these characters correspond to a representation of the point group, and is it reducible? Well, if it is a representation, it is certainly not irreducible. It's a reducible representation. Why? Because the character for the identity is 4. And the character for the identity class tells you the dimensionality of the representation. So this is a 4-dimensional representation. For each one of the symmetry operations, you have 4x4 matrices, right? And this cannot be an irreducible representation of the group, because you can already see here in the character table that for this particular group you have 4 1D representations and 2 2D representations. You cannot have a 4-dimensional representation for this group. Okay. Another way to see that is by looking at this relation here. And age is the order of the group. In this case, 1, 2, 3 is 12. Age is equal to 12. So you cannot have a 4x4 representation because 4 squared is 16. It's larger than 12. Okay, so if it is a representation, then it is reducible. How can I find out if this is a reducible representation of the group or not? So I can work with the decomposition of the characters of a reducible representation into a linear combination of characters of irreducible representations of the group, right? If you remember, if you have a reducible representation, the character for a certain class can always be written as a linear combination over all different representations with coefficients AI of the characters of the irreducible representations for the same class CK. And these coefficients AI, they are uniquely determined, they are uniquely defined by this equation here. Sum over classes, number of elements in each class, and the product of characters of the irreducible representation, complex conjugate, times the character of the reducible representation. Let me call it reducible. So you can, what we can do is to work out this formula for all the irreducible representations and to see if we can find these coefficients. If that's true, and we will prove that indeed this representation is reducible, and actually it will show us exactly how it decomposes into irreducible representations. Okay? We can start to do that. Let me do one case first. Let's take, for instance, gamma I equals to the identity representation A1 prime, which is this representation here. Let me do this case first. So if I choose this, then what is the coefficient A for the A1 prime representation? So it's 1 over A, so 1 over 12, and the sum over classes. Now we need to be careful here because we have to multiply three numbers: number of elements in each class and number of the character for both classes. Okay, so for the identity class is 1 times 1 times 4, right? So it's I think it's helpful if I write here. Let me write the characters of the reducible representation. Just 1 second. I can write here the characters for the reducible representation, which are 4 for sigma age is 2, for C3 is 1, for S3 is -1, for C2 prime is 2, and for sigma V is 0. Okay, so the three numbers we have to multiply is this number times this number times this number, in this case 1, which is the number of elements in each class. Okay, so the first time is 1 times 1 plus 4 times 4. The second one is 2 times 1 times 1 plus 1 times 1 times 2 plus -1 times 1 times 2 plus 2 times 1 times 3 plus 0. Okay, so this is 4 plus 2 6 plus 2 8 minus 2 6 plus 6 12 divided by 12. This is 1. So that means this reducible representation, gamma reducible, contains the A1 prime just once. So it's A1 prime plus other representations here. So I could do the same calculation for all the different representations and then to find out this decomposition, right? So okay, this is a straightforward way to do this, but in many cases, if you look very careful at the character table with some experience, you'll be able to guess what are the decompositions that you need. So in this particular case, the result is the following result. You can verify that, but in many cases you can try to guess this decomposition, because there are not many possibilities, right? Oops, O1 prime plus it certainly must be a combination of a two-dimensional representation plus two one-dimensional representations. And if you work out the different possibilities, and you'll be able to see that this reducible representation is actually decomposed into the sum of these three irreducible representations by looking at the characters. Okay. But of course, if you have difficulties in doing that, you can always do the hard way, which is work out this decomposition formula. All right. Okay. So this is the end of this lecture, and we have 3 problems left in this chapter. 2 of them we did as examples today, and we have these 3 problems left that I'm going to leave to you as the next problem set 3, and they are due next Wednesday, and our next lecture is going to be on Monday. Okay. All right, so have a good weekend.